In this video, I want to explain how to draw Lewis structures. Throughout this explanation, I'll start out with a very basic set of steps that can be taken and progress into a more detailed explanation. In the first step, we determine the number of valence electrons that must appear in the structure. In the second step, we determine what atoms are central atoms and what atoms are terminal atoms. All hydrogen atoms are terminal atoms. Central atoms are usually the atoms with the lowest electronegativity. In step 3, we write a plausible skeletal structure. We join the atoms in the skeletal structure by a single covalent bond, or a dash. The single bond in between the atoms, or the dash, represents 2 electrons. In step 4, with the valence electrons remaining, we first complete the octet of the terminal atoms. Then, to the extent possible, we complete the octet of the central atoms. In step 5, if one or more central atoms are left with an incomplete octet, we move the lone pair electrons from one or more terminal atoms to form multiple covalent bonds to the central atoms. And the last and most important step is to verify the molecule is correct. We make sure the number of valence electrons in the final molecule are the same as the number of total valence electrons determined in step 1. Next, we make sure that each atom has a filled outer shell of 8 valence electrons, with the exceptions of hydrogen, as hydrogen only requires 2 electrons for a complete outer shell. I want to run through these steps with a molecule called formaldehyde, which has a formula of CH2O. Formaldehyde was used to go through the steps of Lewis dot structures, so I'll use the same molecule to kind of streamline the difference between Lewis dot structures and Lewis structures. In the first step, we determine the total number of valence electrons that appears in the structure. The formula is CH2O. Starting with carbon, we go to the periodic table and we can find carbon right here, and it has 4 valence electrons. There's 1 carbon, so for that element we have 4 valence electrons. The next element in the formula is hydrogen, which can be found right here on the periodic table. Hydrogen has 1 valence electron. There are 2 hydrogens, so the valence electrons for hydrogen would come out to 2. The next element in the formula can be found right here on the periodic table, and the group number is 6, so oxygen has 6 valence electrons. There's 1 oxygen, so oxygen contributes 6 valence electrons to the molecule. When we add these up, we get 12 valence electrons. So step 1 is complete, and we have 12 valence electrons. In the next step, we determine what atoms are central atoms and what atoms are terminal atoms. So we know that hydrogen atoms are always terminal atoms, so this part of the formula can be put in the terminal category. So from there, we need to determine which atom is a central atom between the carbon and the oxygen. Looking at the electronegativity chart, we can see that oxygen is much more electronegative than carbon. So carbon would be the atom in the formula that is the least electronegative. So we can put that in the central atom category. And oxygen we can put up here in the terminal atom category. In step 3, we write a plausible skeletal structure. We join the atoms in the skeletal structure with a single covalent bond, or a single dash representing 2 electrons. So to start off, we put the atoms in categories and identify the central atom. We identified carbon as a central atom, and the terminal atoms were the hydrogens and the oxygen. So we can begin by putting the hydrogens on the carbon with a single bond, because we know these are going to be terminal atoms. From there, we have the oxygen left. We know oxygen cannot go on any hydrogen because hydrogen can only have 1 bond. So we connect that to the carbon, and we would have this as the skeletal structure. In step 4, we take the remaining valence electrons and first complete the octet of the terminal atoms. Then, to the extent possible, we complete the octet of the central atoms. The first thing we have to do is find exactly how many remaining electrons we have. So we started out with 12 valence electrons, and with each bond in the skeletal structure, there are 2 valence electrons. So we have 1, 2, 3 bonds in the skeletal structure, and 2 electrons in each bond would give us 6 valence electrons that are used up. So we would have 6 valence electrons remaining to distribute. The terminal atoms are the hydrogens, right here and the oxygen right here. We can't distribute the remaining valence electrons on the hydrogen atoms because they have a filled valence electron with 2 electrons. So that means we have to distribute the electrons to the oxygen first. After distributing the valence electrons to the oxygen, we have a structure like this. In the fifth step, if one or more central atoms are left with an incomplete octet, we move lone pairs of electrons from one or more terminal atoms to form multiple covalent bonds with central atoms. So evaluating the atoms, we can see that oxygen has a complete octet with 8 valence electrons. There's 3 sets of lone pair electrons in one bond, which would give it 8 valence electrons. And the hydrogen atoms are connected to the carbon with one single bond. And there's 2 electrons in a single bond, so hydrogen would have a filled outer shell of 2 electrons. Looking at carbon, there are 3 single bonds to carbon, giving carbon 6 valence electrons. We can move a set of lone pair electrons from the oxygen atom in to form a double bond between oxygen and carbon. Once we turn a set of lone pair electrons into a bond between the oxygen and the carbon atom, we can then count those electrons towards completing the octet. So carbon now has 2, 4, 6, 8 valence electrons to give a complete octet to carbon. And oxygen would also have a complete octet with 2, 4, 6, 8 valence electrons, and this would give oxygen a complete octet of 8 valence electrons. The last and most important step is to verify that the molecule is correct. We first make sure that the valence electrons in the final molecule are the same number of total electrons determined in step 1. In step 1, we determined that there's 12 valence electrons. So evaluating the molecule, we can see that we have 2, 4, 6, 8, 10, 12 valence electrons in the molecule. So the first part checks out. In the next step, we make sure that each atom has a filled outer shell of 8 valence electrons, with the exception of hydrogen, as hydrogen only requires 2 electrons for a complete outer shell. And looking at oxygen, we can see there's 2, 4, 6, 8, so oxygen checks out. Carbon, we can see there's 2, 4, 6, 8, so carbon checks out. Hydrogen only needs 2 electrons, and there's 2 for this hydrogen, there's 2 for this hydrogen, so both of these check out. This part of the verification is complete and checks out, so the molecule is correct and verified. This next molecule, I want to draw CO2, carbon dioxide. So our first step is to determine the total number of valence electrons that must appear in the structure. So we can find carbon on the periodic table. Carbon has 4 valence electrons, and there's 1 carbon. The carbon element gives us 4 valence electrons. Next we have oxygen, and finding oxygen on the periodic table is right here. Oxygen has 6 valence electrons, and there's 2 oxygens, so the oxygen element would give us 12 valence electrons, giving us a total of 16 valence electrons for the carbon dioxide molecule. So the valence electrons for CO2 equals 16 valence electrons. So in step 2, we determine what atoms are central atoms and what atoms are terminal atoms. There are no hydrogen atoms, so we won't have to consider this part here. The next part of the guideline says that the central atom is the one that's usually the lowest in electronegativity. Carbon has an electronegativity of 2.5, and oxygen has an electronegativity of 3.5, so carbon would be the center atom. In step 3, it says to write a plausible skeletal structure. We join the atoms in a skeletal structure with a single covalent bond. So with carbon being the central atom, each oxygen atom would have to come off of the carbon like this. It's very important to have excellent bookkeeping when it comes to keeping track of valence electrons and account for all the electrons in the molecule at all times. And for that reason, I added this step so we know exactly where all the electrons are at and exactly what electrons need to be distributed. For this step, it says that for each bond in the skeletal structure, subtract 2 valence electrons from the total number of valence electrons. We said that we had a total number of valence electrons of 16. There are 2 valence electrons in each bond, so that would be a total of 4 valence electrons. So 16 minus 4 would give us 12 valence electrons to distribute. In step 5, it says with the valence electrons remaining, first complete the octet of the terminal atoms, then to the extent possible, complete the octet of the central atoms. So we had a skeletal structure that looked like this. And from step 4, we determined that we had 12 valence electrons to distribute. In step 5, it says to complete the octet of the terminal atoms first. And to the other oxygen, we can give it an additional 6 valence electrons. That would mean that we spent 12 valence electrons and we have 0 valence electrons to distribute to the central atom. So we can move to step 6. In step 6, it says that if one or more central atoms are left with an incomplete octet, move the lone pair electrons from one or more terminal atoms to form multiple covalent bonds to the central atom. So if we look at the central atom carbon, we can see that it only has 4 valence electrons in the outer shell, and it needs 4 more valence electrons to complete the octet. So we can take these lone pair of electrons on the oxygen and use them as bonding electrons, and that would give us a structure that looked like this. Carbon still doesn't have a filled valence electron of 8 valence electrons. It only has 6 valence electrons. So our options are to either go to the other oxygen and distribute the lone pair of electrons on the other oxygen into a pair of bonding electrons, or we can add an additional pair of electrons from this oxygen where we would have a triple bond on this end, and on the other end we would only have a single bond. I'm going to go ahead and go to the other end of the molecule and distribute these lone pair of electrons out to be a pair of bonding electrons, where it'll give us a final molecule that looks like this. I know that this molecule is the correct molecule, but given the guidelines that we've been given so far, we could just as easy write this molecule. As we go along, we'll get into more details that'll help us out when we determine the distribution of the electrons. And the last and most important step is to verify. First, we make sure that the number of valence electrons in the final molecule are the same as the number of total valence electrons determined in step 1. And in step 1, we determined there were 16 valence electrons. So there's 2, 4, 6, 8, 10, 12, 14, 16. So the first part checks out. In the next step, we make sure that each atom has a filled outer shell of 8 valence electrons, with the exceptions of hydrogen, as hydrogen only requires 2 electrons to complete the outer shell. This doesn't have any hydrogen atoms, so we don't have to worry about that. So each atom should have a filled outer shell of 8 valence electrons. So let's start with oxygen. We have 2, 4, 6, 8, so that checks out. Carbon, we have 2, 4, 6, 8, carbon checks out. And the last oxygen, we have 2, 4, 6, 8, so that checks out. So this part checks out for the molecule, and we can say that the molecule is correct and verified. As you draw more Lewis structures, the less dependent you'll be on a stepwise checklist to draw the structure. So what I want to do is fire off a couple simple molecules just to start off, and we can deal with any snags that may come up that aren't specifically drawn out. So first we'll start out with water, H2O. So first we have to determine how many valence electrons are in the molecule. We can start out with hydrogen. We know that hydrogen has 1 valence electron, and there's 2 hydrogens, so this will give us 2 valence electrons. Oxygen has 6 valence electrons. There's 1 oxygen, so that will give us 6 valence electrons for oxygen, and that will leave us a total of 8 valence electrons for water. So in the next step, we can determine the central atoms and the terminal atoms. So we had water, which would be H2O, which is hydrogen and oxygen. We know that hydrogen is always terminal, and the central atom is usually the one with the lowest electronegativity. Oxygen has an electronegativity of 3.5. Hydrogen has an electronegativity of 2.1. So by this reasoning, hydrogen should be the central atom. But we know this rule will supersede the rule with the lowest electronegativity because it can only be bonded to 1 atom. And of course, the central atom needs to be bonded to more than 1 atom. So with that line of reason, we can determine that the oxygen is going to be the central atom, and the hydrogens are going to be connected to the oxygen. We had a total of 8 valence electrons to begin with, and we used up 4 valence electrons when we drew the skeletal structure. So we have 4 valence electrons left to distribute. And this becomes pretty easy because we know that the hydrogens have a filled outer shell with 2 valence electrons, and we can complete that with a single bond. So the only thing left to complete to reach an octet would be the oxygen. And we can see that oxygen only has 4 valence electrons. And we have 4 valence electrons to spend, so that works out perfectly. And we put lone pairs on the oxygen like this. And to verify, we make sure that the valence electrons in the final structure is equal to the determined amount of valence electrons that were required in the first step, which was 8 valence electrons. So we can determine that real quick. We have 2, 4, 6, 8, and that requirement is met. So next, we have to make sure that each atom has a complete octet of 8 valence electrons, with the exceptions of hydrogen. They only need 2 valence electrons. The hydrogens have 2 valence electrons, and we have 2, 4, 6, 8 valence electrons for oxygen, and oxygen has met those requirements, so we can say that this molecule is correct and verified. Another aspect to consider when drawing Lewis structures are molecules that hold a charge. An example of this would be the ammonium ion, which holds a charge of 1. We look at this in the first step where we determine the total number of valence electrons. We said the ammonium ion was NH4+, and nitrogen has 5 valence electrons, and hydrogen has 1 valence electron. So nitrogen has 5 valence electrons, there's 1 nitrogen, so we have 5 valence electrons from nitrogen. Hydrogen has 1 valence electrons, and there are 4 hydrogens, so that's 4 valence electrons from the hydrogens. How we deal with the charge is when a charge is positive on the molecule, we subtract an electron, and when a charge is negative, we add an electron. So this is a positive charge of 1, so we would subtract an electron. The charge of a molecule is completely dependent on the addition or subtraction of electrons. The positive charge does not change. So in this arbitrary model, if we had 4 positive charges and 4 negative charges, and we would subtract a negative charge, the overall charge would be positive 1, because each negative charge would cancel out the positive charge. And if there was a positive charge left with no negative charge to cancel it out, then the positive charge would remain and give us a positive charge of 1. Conversely, if we would add a negative charge, when we cancel out these charges, we would have a negative charge remaining. So we would end up with a negative charge overall. So in the case of the ammonium ion, where it has a positive charge, we subtract a valence electron. And that's how we get a total of 8 valence electrons. So step 1 is complete. Moving on to step 2. So the next step of determining the arrangement of the atoms and connecting them with a single bond is pretty easy. We know that the hydrogen atoms are always terminal, and the nitrogen would be the central atom. So we can connect each hydrogen to the nitrogen with a single bond. When we do this, we use up all the valence electrons and the bonds. We have 2, 4, 6, 8. So the structure is complete. And to account for the positive charge, put brackets around the structure and put a positive charge on the upper right hand corner. So at this point, we don't have to go on to step 3 because the requirements are satisfied for the Lewis structure. So in the beginning, we started with a very rough outline of how to draw a Lewis structure, and from there we went on to different components that can be added when drawing a Lewis structure. Now we can collect everything we know about drawing a Lewis structure and develop a strategy from start to finish with everything we've went over. Number 1, determine the total number of valence electrons that must appear in the structure. Number 2, subtract electrons with every positive charge and add electrons with every negative charge. Number 3, determine what atoms are central atoms and what atoms are terminal atoms. All hydrogen atoms are terminal atoms. With central atoms, we usually take the atoms with the lowest electronegativity. Number 4, we write a plausible structure. We join the atoms in a skeletal structure by a single covalent bond. Number 5, for each bond in the skeletal structure, subtract 2 valence electrons from a total number of valence electrons. Number 6, with the valence electrons remaining, first complete the octet of the terminal atoms. Then, to the extent possible, complete the octet of the central atoms. Number 7. If one or more central atoms are left with an incomplete octet, move lone pair electrons from one or more of the terminal atoms to form multiple covalent bonds to the central atoms. The 8th and most important step is to verify. Make sure the number of valence electrons in the final molecule are the same as the number of total valence electrons determined in step 1. After that, make sure that each atom has a filled outer shell of 8 valence electrons, with the exceptions of hydrogen, as hydrogen only requires 2 electrons to complete the outer shell. Let's go over a few structures using this new checklist to write Lewis structures. Let's first try ethylene, and it has a formula of C2H4. First, we have to determine the total number of valence electrons. Pulling up a periodic table, we said the formula was C2H4. So carbon is right here, the 4th group, which would indicate it has 4 valence electrons, and hydrogen is right here, first group indicating it's got 1 valence electron. So starting off with carbon, it has 4 valence electrons, and it has 2 atoms, giving us 8 valence electrons. Hydrogen has 1 valence electron. It has 4 hydrogens, so that would give us 4 valence electrons, giving us a total of 12 valence electrons. So step 1 is complete with 12 valence electrons. Moving on to step 2, there is no charge, so we can skip step 2. Step 3, we determine what atoms are central atoms and what atoms are terminal atoms. We know that the hydrogen atoms are always terminal atoms, so the carbon atoms must be central atoms. So step 3 is complete. So in step 4, we write a plausible skeletal structure to join the atoms by a single covalent bond, which is represented by a single dash. The hydrogen atoms are the terminal atoms, so we start with the central atoms, and there's only 2, so we write the 2 carbon atoms with a single bond between them, and there are 4 hydrogen atoms, so we join those to the carbon with a single bond, and we have this structure. Step 4 is complete. In step 5, for each bond of the skeletal structure, we subtract 2 from the total number of valence electrons in step 1. So we determined that there were 12 valence electrons in the molecule. There are 1, 2, 3, 4, 5 bonds in the skeletal structure, and each bond has 2 valence electrons. We subtract that from the total number of valence electrons, which would be 12. So 12 minus 10 is 2. So step 5 is complete. Moving on to step 6, with the valence electrons remaining, first complete the octet of the terminal atoms, then to the extent possible complete the octet of the central atoms. And at most, hydrogens can only form 1 bond, so these outer shells are complete for all the hydrogens. And the only atoms or elements at this point that are incomplete would be the carbon atoms. And we have 2 valence electrons, so we place those on one of the carbon atoms. Remembering these have to be placed on the atom in pairs, so we can only put it on one carbon atom. So step 6 is complete. Looking at step 7, if one or more central atoms are left incomplete in the octet, move the lone pair electrons from one or more terminal atoms to form multiple covalent bonds to the central atom. Since the terminal atoms, hydrogen, are complete, we start with the pair of electrons on the central atom, but we do the same thing. We can see this carbon has a complete octet. It has 2 lone pairs and 3 bonding pair electrons, but this carbon only has 3 bonding electrons. So we move the lone pairs from this carbon to form a double bond, which then gives us a structure that looks like this. A feature that's held in the bonding electrons is that whatever they are bonding to counts towards the completion of an octet in both atoms. So now we have a double bond, and these electrons will count towards the completion of the octet in this carbon and in this carbon. When before we had a lone pair of electrons, and the lone pair of electrons will only count towards the completion of the octet in the atom that they're attached to. So step 7 is complete. And we now have a structure of ethylene that looks like this. And the last and most important step is to verify what is required for a Lewis structure. So the first part is to make sure that the number of valence electrons in the final molecule are the same as the number of total valence electrons in the first step, which would be right here, and we had 12 valence electrons. And the next part is to make sure each atom has a filled outer shell of 8 valence electrons, the exceptions of hydrogen, as hydrogen only requires 2 electrons for a complete outer shell. These guidelines, let's go ahead and quickly evaluate evaluate this molecule. So we determine the first step that there are 12 valence electrons right here, and in the molecule there are 2, 4, 6, 8, 10, 12, so this part of the guidelines are met. In the second part, all the hydrogens have a filled outer shell of 2 electrons with a single bond right here, and there's 4, so that part is met. And each carbon has 8 valence electrons from each bond. This carbon has 2, 4, 6, 8. This carbon has 8 valence electrons, and this carbon has 2, 4, 6, 8. So this carbon has met the requirements of 8 valence electrons. So the second part is met, and finally you can say the requirements for a proper Lewis structure has been met.